A 250-kilometer-per-hour bullet train is right now accelerating beneath the East China Sea, not a prototype. The Jintang Tunnel opened on December 30th, 2022. It runs 16.2 kilometers end-to-end, with 10.87 of those kilometers driven directly under the seabed. As of May 2026, more than 45 million passengers have already made the crossing. The future of undersea transit is not being studied somewhere. It is already operational on a Tuesday morning commute in eastern China. The price tag was 16.8 billion yuan, roughly $2.5 billion US. Groundbreaking came in September 2017. Revenue service began on December 30th, 2022. 5 years and 3 months from first dig to first passenger. Western proposals for comparable undersea high-speed rail sit unbuilt, stalled in feasibility committees and environmental review. The contractor behind Jintang is China Railway Construction Corporation, the same state-owned giant that built much of the national high-speed rail spine. This is not infrastructure as consumer convenience. This is infrastructure as raw state capacity, deployed at the speed only a centralized industrial system can sustain. And the conditions it was deployed into were brutal. 0.6 megapascals of seawater. Picture the deep point of the Jintang Tunnel, 78 meters below the surface of the East China Sea. The water above is pressing down on the tunnel lining with a force of 0.6 megapascals, 6 times standard atmospheric pressure. Every square meter of tunnel wall is holding back a column of seawater that, if it failed, would not leak. It would explode inward. And the engineers knew that from day one. The geology along the underwater section is not a single, predictable material. It is 18 separate fault zones. The seabed shifts from soft marine silt, the kind of material that behaves almost like wet clay, to fractured bedrock and back again, sometimes within a span of just a few meters. A boring machine cutting through soft silt behaves one way. The same machine, minutes later, hitting fractured rock, behaves entirely differently. The pressure on the cutter head changes. The waste removal rate changes. The risk of a sudden water inrush changes. Here is the thing most engineers outside China have said quietly for years about undersea rail at this speed. The margin for error is essentially zero. A road tunnel under the sea can tolerate a slow leak, a partial closure, a phased repair. A high-speed rail tunnel at 250 kilometers per hour cannot. The train is moving at nearly 70 meters every second. A single uncontrolled water ingress event, and the entire system floods in minutes. The Western precedent everyone reaches for is the Channel Tunnel between England and France. 50 kilometers long, a genuine engineering landmark. But the Channel Tunnel carries Eurostar trains at a maximum of 160 kilometers per hour through its undersea section, not 250. The aerodynamic loads at 250 kilometers per hour inside a confined tunnel are an entirely different physics problem. Pressure waves slam against the tunnel walls. The trains themselves act like pistons pushing columns of air. The lining has to absorb those cyclical loads for 100 years without cracking. And those loads are happening while 0.6 megapascals of seawater are pushing in the opposite direction. The fault zones add another layer. Each fault is a potential water pathway, a crack in the rock that, under pressure, becomes a pipe. The tunnel had to be sealed, not just along its length, but across every geological boundary it crossed. Grouting campaigns ran continuously during construction. Cement slurry was injected ahead of the cutter head to stabilize the ground before the machine even touched it. Behind the cutter head, precast concrete segments were installed and locked into rings, and the gap between those rings and the surrounding rock was filled and sealed again. Every meter of this tunnel is a negotiation with the sea above it, and the East China Sea is not a calm partner. Typhoon season brings storm surges that change the pressure profile at the seabed. Tidal cycles flex the rock around the tunnel, twice a day. Shipping traffic overhead, including some of the heaviest container vessels on Earth bound for the port of Ningbo Zhoushan, the busiest cargo port on the planet by tonnage, adds dynamic loading that ripples down through the water column. The Jintang Tunnel was designed to absorb all of it for a century, without a single failure event. Every other country looking at undersea high-speed rail has, until now, stopped at the feasibility stage. Because of exactly these pressures, exactly these geologies, exactly these margins. China did not stop. China built the machine that could cut through it. The machine has a dimension that tells the entire story. 14.57 meters. That is the diameter of the shield tunnel boring machine that carved the underwater section of Jintang. At the time of its deployment, it was the largest shield TBM ever used for an undersea rail project anywhere on Earth. To picture 14.57 meters, imagine a 4-story building lying on its side, slowly rotating, grinding forward through rock and silt at a rate measured in meters per day. The cutter head is studded with hardened steel teeth and disc cutters designed to shred through fractured bedrock. Behind it is a sealed chamber that holds the excavation face under pressure, matching the pressure of the seawater above so that nothing flows in. Behind that chamber is an erector arm that picks up precast concrete segments, each weighing roughly 12 tons, and bolts them into rings that form the tunnel lining as the machine advances. Every revolution of the cutter head is a controlled event. Too much forward thrust and the seal at the face breaks. Too little and the machine stalls in soft silt. The operators are not driving a vehicle. They are managing a continuous pressure equilibrium between a 14.57 meter steel face and the open ocean 3 stories above them. And they are doing it while crossing 18 fault zones. The conceptual foundation for this kind of work in China traces back through decades of academic research. The late academician Wang Mengshu, one of the most influential figures in Chinese tunnel engineering, spent the years before his passing in 2018 building the theoretical framework for ultra-large undersea shield tunneling. His work on segmental lining design, on grouting strategies for marine geology, on the behavior of TBMs under high water pressure, fed directly into the specifications that Jintang would later require. He did not live to see the train run. The framework he built did. The on-site execution fell to Chief Engineer Chen Xiangsheng and his team at China Railway Tunnel Group. They had to switch grouting recipes on the fly when the seabed composition shifted. They had to maintain forward progress, while the cutter head teeth wore down faster than expected in the harder rock sections, requiring planned interventions to swap them out under pressure, hundreds of meters below the seabed. There is a procedure for this: hyperbaric chamber access. Workers in pressurized suits, breathing controlled gas mixtures, entering the cutter head chamber to replace components while the surrounding ground is held stable by the machine itself. It is the underwater equivalent of changing the tires on a moving car. China has now done it at this scale, repeatedly, on a single project. The 14.57 meter dimension allowed the tunnel to accommodate the full system's envelope: ventilation ducts, power and signaling conduits, drainage channels, evacuation walkways, emergency utilities, all of it inside a single bore. One machine, one bore, 10.87 kilometers under the sea. But cutting the tunnel was only the first promise. Keeping it alive for 100 years was the second. The design brief for Jintang was not a 50-year tunnel. It was a 100-year tunnel. That number is not marketing. It is a structural specification written into the materials, the lining design, and the monitoring architecture. Seawater corrosion is the slow assassin of any undersea structure. Chloride ions migrate through concrete over decades, reaching the steel reinforcement inside. And once they reach it, the steel begins to rust. Rust expands. Expansion cracks the concrete. Cracks let in more water. The cycle accelerates. Most undersea tunnels are designed for 50 to 100 years on paper, but with significant remediation cycles built into the assumption. Jintang was designed to resist the chloride migration itself for the full century through multi-layer waterproofing membranes, high-density concrete formulations with supplementary cementitious materials, and sacrificial protective coatings on the most exposed segments. The lining is not a single barrier. It is a system of barriers, each one designed to fail gracefully into the next. But materials alone are not enough at this depth and at this speed. The tunnel had to know its own condition at every moment, so the engineering team embedded more than 2,400 sensors directly into the structure. Fiber optic strain gauges along the lining segments, pressure transducers at the segment joints, temperature sensors tracking thermal gradients between cold seawater outside and the warmer tunnel interior, seismic accelerometers measuring vibration from passing trains and from the natural movement of the seabed itself. All of that data flows in real time to a central control system. The system does not just record, it predicts. Machine learning models trained on the baseline behavior of the tunnel watch for anomalies. A pressure reading that drifts slightly, a strain pattern that deviates from the model, a temperature shift that suggests moisture migration. The system flags it before it becomes a problem. The evacuation architecture matches the same logic. Cross passages connect the main tunnel to a parallel service tunnel every 750 meters. That spacing is deliberate. At 250 kilometers per hour, a train covers 750 meters in about 10 seconds. In an emergency stop, passengers are never more than a few minutes' walk from a sealed evacuation route. The cross passages themselves are pressurized to prevent smoke or water from migrating between bores. Lu Chunfeng of China Railway Tunnel Group described what Jintang represented as the mastery of the most complex underwater engineering challenges. That phrase was not delivered as celebration. It was delivered as a status report. The capability has been acquired. The next project will inherit it, and the people riding the trains have already felt the result. Before December 30th, 2022, the trip between Ningbo and Zhoushan was a study in friction. Zhoushan is an archipelago, more than 1,000 islands scattered across the mouth of Hangzhou Bay. For most of modern Chinese history, getting to the main island of Zhoushan from the mainland meant a ferry crossing, a long detour by road, or a combination of both. The Zhoushan Cross Sea Bridge, completed in 2009, cut the road journey to roughly 90 minutes under good conditions, longer in bad weather, longer still during typhoon shutdowns. 90 minutes is not just an inconvenience, it is an economic boundary. It is the difference between a city that participates in the Yangtze River Delta economy and a city that watches it from across the water. Zhoushan, with a population of around 1.16 million, has been historically defined by what it could not easily reach. The Ningbo Zhoushan Port, the highest tonnage cargo port on Earth, sits split between two administrative regions precisely because the geography forced the split. The Yangzhou high-speed rail line collapses that 90-minute road journey into 27 minutes of rail travel, a reduction of roughly 70%, and critically, the 27-minute figure is not weather-dependent the way the bridges are. The train runs in the typhoon. The train runs in the storm surge. The tunnel does not care what is happening on the surface of the East China Sea. Time compression of that magnitude rewrites the rules of where people live and where they work. A worker on Zhoushan can now hold a job in Ningbo's urban core. A medical specialist in Ningbo can see patients on Zhoushan in the morning and be back in the operating theater by lunch. 45 million passenger journeys have already been recorded as of May 2026, and the ridership curve is still climbing. The Yangzhou line connects Ningbo into the existing national high-speed rail network. A passenger on Zhoushan is not just connected to Ningbo. They are connected to Shanghai 2 hours away, to Hangzhou 90 minutes away, to the entire eastern seaboard rail spine. And the line is not a dead end. It is a beginning. The Jintang Tunnel did not arrive in isolation. It arrived as the proof of concept for a deliberate sequence of undersea infrastructure projects rolling out along China's coast, each one feeding lessons into the next. The clearest immediate successor is the Shenzhen-Zhongshan Undersea Corridor in the Pearl River Delta, a 24-kilometer link with a 6.8-kilometer undersea section currently targeting completion in 2027. The Shenzhen-Zhongshan project draws directly on what Jintang proved was possible. The engineering review boards reference Jintang specifications when setting requirements. The waterproofing protocols are inherited. The embedded sensor architecture is inherited. The 100-year design specification is inherited. The personnel are, in some cases, the same engineers redeployed from the East China Sea to the Pearl River estuary. When the corridor opens, it will cut the journey between Shenzhen and Zhongshan from roughly 2 hours to under 30 minutes. The same time compression pattern as Yangzhou, the same labor market integration logic. Two of China's most economically productive coastal city clusters being stitched together by undersea infrastructure built on a common engineering playbook. The replication does not stop there. The planned Bohai Strait crossing, connecting Shandong and Liaoning, the ongoing studies for additional cross-strait rail links, all of these inherit elements of what Jintang established and Shenzhen-Zhongshan is refining. The state has a workforce. The state has a supply chain. The state has a sensor and monitoring industry that grew up servicing these projects. Every new tunnel is cheaper, faster, and more confident than the one before it. This is the part other countries do not have. Not the engineering itself, the institutional muscle to execute the engineering repeatedly. A British or American firm could, in principle, design a tunnel like Jintang. They could not, in practice, mobilize the procurement, the workforce, the financing, and the political continuity to build it on a 5-year timeline at the cost China achieved. And that institutional muscle is now being pointed at something that, even 5 years ago, sat firmly in the category of engineering fantasy. Feasibility studies are already underway for a 135-kilometer undersea rail tunnel beneath the Taiwan Strait, with a speculative target horizon around 2035. If built, it would be the longest undersea rail tunnel on Earth by a wide margin. The engineering challenge dwarfs Jintang by an order of magnitude. The Taiwan Strait is deeper. The seabed is seismically active, sitting near the boundary of the Eurasian and Philippine sea plates. The route would cross fault systems orders of magnitude more complex than the 18 faults at Jintang. Every undersea tunnel China has built before this one starts to look, in retrospect, like a training exercise. No comparable operational undersea high-speed rail project exists in the United States, the European Union, or Japan. None are under construction. None are in advanced planning. China now holds the operational data, the trained workforce, the supply chain, and the institutional confidence to keep building. Infrastructure capability compounds. Each project lowers the cost of the next, and the undersea rail doctrine is becoming exportable, the same way the high-speed rail playbook became exportable a decade ago. The tunnel under the East China Sea is not the achievement. The capability to build the next one is.